So in this video we are going to discuss the question in thermal and statistical physics which appeared in CSIR JRF examination that occurred in June 2015. Okay, the first question is by reading the accompanying graph, determine the incorrect statement out of the following. Okay, so we have to identify the wrong statement among the given four statements. Okay, so we are given a graph between pressure and temperature. That's a phase diagram. Okay, so from here such kind of phase diagram, because it's given to a solid, liquid and gas phase of a particular system. So if you just take a look at the closest Clapeyron equation, that is dP by dt, that is equal to L by T B2 minus B1. So here B2 and B1, these are the specific volume corresponding to the final phase and the initial phase. B1 corresponds to initial phase and B2 is the specific volume of the phase after phase transformation. Okay, so depending upon the sign of this dP by dt, we can predict whether the melting point or the boiling point is going to increase after the phase transformation has taken place. So let's first try to understand the effect of pressure on boiling point. The first point, influence of pressure on boiling point. Okay, so when we talk about the phenomena of boiling, so that means after for instance, let's talk about the water. So when water boils, its volume changes from B1 to B2. Okay, so after boiling, the volume B1 that corresponds to the liquid phase of water and it changes into vapor. So this implies that V2 is greater than V1. Okay, so therefore the right hand side of the equation 1, it is a positive quantity for this situation. So that means in order to keep the left hand side also positive, suppose pressure increases. Okay, suppose pressure increases, that means the final pressure and the initial pressure, that is P1, they are connected like this, because P2 it's larger than P1, so that means pressure is increasing. Okay, so to make the left hand side positive, this implies T2 should be greater than T1. So that means the final boiling point of the phase that's going to be larger than the boiling point of the initial phase. Okay, so that means there is a increase in boiling point. Okay, so that means let's take a look at the options which are given to you. The boiling point increases with the pressure, so therefore option C is correct here. So I will mark it, in fact we have to identify the incorrect statement, so I will mark it with the this sign. So this is a correct statement, boiling point increases with the pressure. So first correct statement we have identified. Now let's take a look at the point D. Solid, liquid and gas can coexist at the same pressure and temperature. So basically this statement D talk about this point here, this one, where both all three phases, that is solid, liquid and gases, they coexist together. So that means this is point D is also correct. Okay, now let's take a look at the melting point, that how melting point is influenced. Okay, so let's try to understand the influence of pressure on melting point. Okay, so here we will have two different situations in order to predict the influence of pressure on the melting point. Okay, so we will make use of the same equation to predict the dependence of the melting point on the pressure. So the first case that I am going to talk about, it is the situation when a particular substance, when it melts, what its volume it increases. Okay, so for instance, so that means when V2 is larger than V1, so that means upon melting of substance expand. Okay, for instance wax, the examples are wax and sulfur. Upon melting, these two substances, they expand. So when V2 is larger than V1, so then again V2 minus V1 will be a positive quantity, and therefore right hand side of equation 1 will be a positive quantity. Okay, so that ensures that the left hand side is also going to be positive. So that means if the final pressure is larger than initial pressure, this ensures that T2 is larger than T1. So that means for such a substance which expand upon melting, so the melting point increases with increase in pressure. Okay, now for the second case, the case B, when V2 is smaller than V1. So this is the situation when upon melting a substance contract. Okay, example is ice water system. Okay, so when ice it melts, so the volume, if you just notice the volume of the ice cube, then and then after melting, when it's changed into water, and just take into consideration the volume of the melted ice, then we will find that the volume of the water that's smaller than the volume of the ice. Okay, so in this situation, B2 minus B1, that will be a negative quantity. So this means when there is an increase in pressure, when P2 is larger than P1, so this implies T2 will be smaller than T1, so that T2 minus T1 become a negative quantity. Okay, so this means when with increase in pressure, the melting point reduces for the substance which contract upon melting. So therefore dP, for such a case, dP upon dt will be negative, and the melting point of such a substance will reduce. Melting point for such a case will reduce. Okay, so now here if we just take a look at this curve, it's a phase transition between the solid and liquid phase. So here this line, it falls in the second quadrant, and it's if you just take into account the slope of this line, so for this line dP by dt is negative. DP by dt, it is negative. Okay, so that means for this particular case, this statement will be valid. That's melting point of for the given phase diagram, it will reduce with an increase in pressure. So here in the statement A, it's written that melting point increases with pressure. So that means this is the incorrect statement here. So here incorrect means this is the right answer here for the given question, because we have to identify the incorrect statement. Okay, so this is going to be a correct statement for the diagram. So that, let me draw the diagram here. Option A will be correct for the diagram that I'm drawing here. Okay, if we are having a phase diagram something like this, if I'm calling this as the common point, that's the triple point. So then if we are having a solid liquid boundary like this, solid, liquid, and then vapor, you can say. Okay, so here solid and liquid boundary, it's having a positive slope. Okay, so this line, if it's a pressure versus temperature graph, so for the solid liquid boundary, dP by dt is positive. So this positive slope ensures that melting point will increase with increase in pressure. Okay, so I hope now the point is clear. Okay, so here correct option is A, which is the incorrect statement describing the given diagram. So let's continue with the next problem. The statement is a system of n distinguishable particles, each of which can be in one of the two energy levels 0 and E. So we are given a system of n distinguishable particles, and we are supposed to distribute them in two energy levels whose energy is given as 0 and E. Okay, it has total energy Ne. Okay, so total number of particle is given to be total number of particles, that is equal to capital N, and total energy of this system, that is equal to small n multiplied by E. Okay, so this means if out of these n particles, total capital N particle, we have to place small n particle here, and this these small n particle will satisfy this constraint, the constraint of total energy of the system to be equal to n times small e. Okay, so therefore the possible number of microstates, you can see the accessible microstates to the system, it's n factorial. Okay, and out of these n factorial arrangements, we have to pick these n particles. So out of total n particle, we have to pick n particles, or we are supposed to fix these n particles in energy state E. So the corresponding arrangements will be n factorial and remaining n minus n factorial. So that will give this will give us the total number of accessible microstates to the system. Okay, so now once the microstates, they are known to us, then the corresponding entropy of the system, it's given by Boltzmann definition of the entropy. And what is that? It's Boltzmann definition of entropy, and which correlate a macroscopic parameter, which is the entropy, with the microscopic parameter, which is number of microstate. S is equal to kb ln omega. So therefore with the help of this equation, the entropy of the system comes out to be equal to kb ln n factorial divided by small n factorial into n minus n factorial. So that means the entropy, it's proportional to ln n factorial upon small n factorial into n minus n factorial. So therefore D is the correct option here. So let's take a look at next problem. The statement is a system of n non-interacting classical particles. Okay, so non-interacting means it's a system of free particle. Okay, so non-interacting implies that non-interacting means it's a system of free particles. Okay, each of mass m, it is in a two-dimensional harmonic potential in the form. Okay, so it is subjected to a two-dimensional potential, which is given of this form, where alpha is a positive constant. The canonical partition function of the system at temperature T, where T is connected with the beta through this relationship. Okay, so first of all, let's try to construct the Hamiltonian of this system, and then we can immediately write the expression for the partition function. So we are given that the given system of particles, it is subjected to this external potential, which is of the form alpha x square plus y square. Okay, so let's call this as equation 1. So because it's a system of free particles, so that means it will have the kinetic energy, and it's a two-dimensional motion. So the corresponding Hamiltonian of this system is given as, it is p square upon 2m plus the external potential, which is given to us. Okay, so for a two-dimensional problem, this becomes px square plus py square by 2m plus alpha into x square plus y square. So that's the Hamiltonian of the system. Now by knowing the partition function, now we can write by knowing the Hamiltonian, we can immediately write the expression for the partition function. Okay, the partition function for one single particle is given as q1 t v, that is equal to 1 upon h square, because it's in two dimension. So and minus infinity to infinity. So we will have 4 integral, basically 2 corresponding to the space integration and 2 corresponding to the integration with respect to momentum space. Okay, minus infinity to infinity, minus infinity to infinity, and then the fourth one minus infinity to infinity, and then exponential minus beta multiplied by the Hamiltonian of the system, which is px square plus py square divided by 2m plus alpha x square plus y square multiply by then dpx, dpy and dx dy. So from here we can obtain the partition function. Okay, so now what we are going to do is we are going to split the terms in the partition function. So I can rewrite it. Okay, so this q1 tv, so that is equal to, so I'm taking 1 by h square outside. Okay, and then inside the bracket we will have the first integral. So I'm not rewriting these limits again and again. So they should be understood from this the first equation. So minus infinity to infinity, and then the first term exponential minus beta px square upon 2m, and then dpx, the second integral with the limit minus infinity to infinity, and exponential minus beta py square upon 2m dp by minus infinity to infinity exponential minus alpha beta x square dx minus infinity to infinity exponential minus alpha beta y square dy. Okay, so these are the four integrals that we are supposed to solve. Okay, so these integrals can be solved by making use of one standard result. So that I'm writing here on the right hand side. The standard result is that the value of the integral minus infinity to infinity exponential minus alpha x square dx, where alpha is a constant here. So alpha is a constant here, that is equal to under root pi by alpha. Okay, so alpha, please note that here alpha, it's a constant here. So here in the first integral, alpha value is equal to beta upon 2m, that is alpha here. So therefore by applying this result, so let me call this as equation 3, and let me call this result as equation 4. Now we want to apply result 4 in equation 5. Okay, so for the first integral I am writing 1 upon h square outside. Okay, so now we will apply equation 4 to the first integral, and by applying this what we will get is, it is under root pi by alpha. Okay, so under root pi by alpha that will give to us, it will become 2 pi m kbt and its power 1 by 2, and root pi divided by beta divided by 2m, so that will give 2m pi divided by beta, so that is equal to 2 pi m kt power 1 by 2. Similarly the next integral will also give us the same expression, 2 pi m kbt power 1 by 2, and from here it's here in place of alpha we are having alpha beta here. So we will apply the same definition again, and this the third integral will give us, so this multiply. So for the third integral we will obtain pi divided by alpha beta and its power 1 by 2, its power 1 by 2, and from the fourth integral also the results that will obtain under root pi by alpha beta and its power 1 by 2 bracket close. Okay, and now we have to simply adjust the terms, and after rearranging all the terms, the final result that we will obtain, so that is equal to q1 tv, so that will give us the partition function basically for single particle. Okay, so after solving it, the results that we will obtain, that is 2m pi square upon alpha beta square and then multiply by 1 by h square. So that's a single particle partition function. Okay, because the particles, they are distinguishable. So simply the n particle partition function can be written as Qn Tv, that is equal to Q1 Tv power n. Okay, so that means Qn can be written as 1 by h square into 2m pi square upon alpha beta square and its power n. So if we just take a look at the options which are given to us, the most appropriate option is the option D here, because there is no factor of 1 by h square here. Okay, but in pencil we cannot get rid of the factor of 1 by h square, but the rest of the expression it matches directly with the expression that we have obtained. So therefore here option D is the correct one here. The condition for liquid and vapor phases of a liquid to be in equilibrium is given by the approximate equation. So the equation is dp by dt dp by dt, that is equal to ql upon t b vapor. That's basically the classic Clapeyron equation. So here V vapor is the volume per particle in vapor phase. So it corresponds to volume per particle in vapor phase. Okay, and QL is the latent heat. Okay, which may be taken to be constant. Okay, if the vapor obeys the ideal gas law, which of the following plot is correct? Okay, so we are given that vapors obey the ideal gas law. So that means we can write that V vapor, that is equal to RT upon P. Okay, so let's call this as equation 2. So 1 and 2 implies that I can write dp by dt, that is equal to by substituting V vapor, that's RT by P. So this is equal to P multiplied by QL. QL is the latent heat, it's given to us. Okay, divided by RT square. Or this can be rearranged by separating the variables dp by P, that is equal to QL upon R T square dt. Okay, so upon integration this equation yields after doing the integration, so that means by doing the integration, so this equation implies ln P is equal to QL upon R into minus 1 by T plus constant of integration. Okay, or it can be rewritten as ln P, that is equal to some constant C which absorb QL and R, QL by R, which is C, and then divided by T plus some constant of integration. Okay, now we will try to understand the qualitative plot that can be obtained from the equation 3. So for this case we will consider two extreme cases. So first is when temperature approaches infinity, so that means that when temperature is quite large. So in that case the term C by T that will approach 0, and then we will have ln P, that's equal to some constant value which is determined by the some constant of integration. So okay, so we assume that it's a constant a positive quantity. So then so in that case ln P is equal to a constant quantity. Okay, but remember that from the we can determine this constant of integration only from the some given condition, and it's possible that it could be a positive quantity or it could be a negative quantity. We are not sure about it. Okay, in the second case when temperature approaches 0, okay, and in that case ln p will approach minus infinity. So then this term will not dominate, then this will be the dominating term. Okay, so when t goes to 0, so c by t, that will approach to minus infinity because of negative sign here. Okay, so that means if you just take a look at the graphs which are given to us, okay, for very large value, so here ln p, it acquires a positive value, and for the when the temperature approaches 0, so that means when we are moving like this, when temperature is approaching 0, then ln p, it become a infinitely large along the negative direction. Okay, so that's the first point. Okay, and in the second case, when when temperature is very large, because we said that ln p, it's equal to constant quantity, so this is also one of the possibility, because we are not sure about that whether this constant of integration it's having a positive value or negative value. So depending on that situation, either option A or option C could be the the correct choices here. Okay, so both of these possibilities could exist depending upon the value of the constant of integration. If it is a positive constant, then C is the correct choice, and if constant of integration, it's a negative constant, then option A will be the correct choice. Let's continue with the next problem. It's related to the Ising model. The statement is, consider 3 Ising spins at the vertices of a triangle which interact with each other with the ferromagnetic Ising interaction of strength J. Okay, the partition function of the system at temperature T is given by. Okay, so we are given a system of 3 spins where the 3 spins, they are placed at the vertices of a triangle. Okay, so first of all, let's try to understand that how many microstates are feasible for such a system, because each spin can align either upward or downward. Okay, so let's try to figure out that, because there are two possibilities for each spin. So that means first spin has possibilities that are equal to 2. Similarly, second spin has the 2 possibility, third spin will have also the 2 possibilities. So in total, the total number of possibilities are, or the arrangements are, that is equal to 8. Okay, so basically the general rule is that it is 2 power 3. Okay, so 2 power the number of spins, so that is equal to 8. So now let's try to figure out all those arrangements. So I'm drawing a triangle, and then we are going to place the spins on these triangles. Okay, so because we require 8 configurations, so 4, 5, 6, 7, and then 8. Now we have to fix the spins on this on the vertices of the triangle. Okay, so in the first case, okay, so the first situation could be that all the spins, they are pointing in the upward direction and they are placed on the vertices of the triangle. Okay, in the second case, all the spins could point in the downward direction. Okay, this is second microstate. Okay, in the third case, the possibilities are, so 2 spins, they are pointing in the upward direction and one of them is pointing in the downward direction. Okay, in the next case, one's pointing in the upward direction and 2 spins pointing in the downward direction. So this way we can generate all 8 microstates. Let me draw them. Okay, and then in the downward direction, so we are having 5. Now the sixth one could be, okay, something like this, 2 pointing in the upward direction. Okay, and then the last one down, and then down, and then up. Now what we will do is, we will evaluate the energy of interaction between the spins. But if you just notice here, we need to apply here the closed boundary condition. Okay, that's important point to note here. We have to apply closed boundary condition. So that means here this spin can interact with this spin, okay, and this spin can also interact with this spin, and this can interact with this spin. So therefore if we label them as S1, S2 and S3, okay, so the total Hamiltonian for this microstates will be H, that is equal to minus J, because it's given that they interact with the ferromagnetic Ising interaction of strength J. So that's why here we are writing the interaction energy as minus J into S1 dot S2 plus S2 dot S3 plus S3 dot S1. Okay, so that will complete the the total interaction energy for this particular configuration. Okay, so in the first case I will do the calculation only for only for two cases, and then remaining calculations can be done in the same way. Okay, so for the first case I am talking about this one. So S1 and S2, both of the spins, they are pointing in the upward direction, and I will assign a number +1 for the spin pointing in the upward direction. So that means what I am saying is that if spin is pointing in the upward direction, I will take it as +1, and if it is pointing in the downward direction, I will assign a number -1 to the spin. Okay, so therefore for the first case I am calling the interaction energy as H1. So that will be equal to minus J S1, that's 1 into 1 plus 1 into 1, because all spins, they are pointing in the upward direction. So I will take S1, S2 and S3 equal to +1. Okay, plus 1 into 1. So this will gives us an interaction energy of minus 3J. So that means for the first case the interaction energy is minus 3J. Okay, similarly we can prove that for the second case the interaction energy is minus 3J. Okay, now let's take another example, the case 3. Okay, so for the case 3 I'm calling the interaction energy as H3. So let me write here for the H2 the interaction energy will be minus 3J, and for this case the interaction energy it's minus J. Now we have called this as S1. S1 and S2, they are pointing in the upward direction. So S1 and S2 +1 into +1 plus what is S2? S2 is +1, and S3 it is pointing in the downward direction. So multiply by -1 plus S3, again it is pointing in the downward direction, and multiply by S1 which is pointing in the upward direction +1. Okay, so this is equal to minus J outside 1 minus 1 minus 1, and that is equal to J. Okay, so that means the interaction energy for the third configuration it is J. Okay, similarly we can evaluate the interaction energy for the other configurations, and you will notice that all rest of the configuration will have the interaction energy of J each. Okay, so this way we notice that among the 8 existing microstates, 2 microstates are having an energy of, so we are having energy Hi, that is equal to minus 3J, and how many microstates are having this energy? 2 microstates. So I will write this result as a degeneracy of 2. Similarly, an interaction energy of J exists, but for how many microstates? 6 microstates. Okay, so now this will allow me to write the partition function for this system. So the partition function for this system, that is equal to Z Gi exponential minus beta Hi, and I taking value from 1 to 8 in principle, because now we have clubbed all the microstates just into 2 energy values. So here the net result will be G1, which is equal to 2 exponential minus beta H1 minus this minus and minus will become plus here, so that will be equal to 3 beta J plus G2, which is 6 exponential and corresponding interaction energy minus beta J. So therefore the our result is 2 exponential 3 beta J plus 6 exponential minus beta J. So that matches with option A here. So therefore option A is the correct answer. So let's continue with the next problem. The statement is, a large number n of Brownian particles in one dimension start their diffusion motion from the origin at time t equal to 0. The diffusion coefficient is given as d. The number of particles which are crossing a point at a distance L from the origin per unit time depends on L and time t as. So we have to identify the correct option out of the given options. Okay, so let's see how we can go through this problem. The diffusion equation for Brownian particle in one dimension is in one dimension the diffusion equation reads nxt divided by dt, and that is equal to d d2 nxt upon dx square. So here d is the diffusion coefficient and nxt equals is the number density. Okay, so the solution for this equation is of the form nxt that is equal to a exponential minus x square upon 4 dt. Okay, so let's call this as equation 2. Now we applying the condition that the total number of particles there, that's equal to the integral from minus infinity to infinity, and then this function nxt dx basically. Okay, so nxt dx, so that means a outside, it's a constant that we have to evaluate by applying this condition, and then exponential minus x square upon 4 dt dx. Okay, so here this is equal to the integral, the value of the integral, it is equal to a outside and its exponential minus alpha x square dx from minus infinity to infinity, and that its value is equal to under root pi by alpha. So that gives us 4 pi dt. So here we have made use of the integral minus infinity to infinity exponential minus alpha x square dx, that is equal to under root pi by alpha. This is standard result. Okay, so from this result, from equation 3 we obtained that a is equal to n upon 4 pi dt. Okay, so that's the value of the constant a. So therefore the solution 2 reduces to, therefore n xt, that is equal to n upon 4 pi dt exponential minus x square upon 4 dt. Okay, so that's the general solution. Okay, so let me call this as equation 4. Now at x is equal to L, the number of particles which are crossing the area at x is equal to L, so this equation becomes n L t, that is equal to n upon under root 4 pi dt exponential minus L square upon 4 dt. Okay, so therefore A is the correct option here. So let's continue with the next problem. The question is from the Bose-Einstein condensation. The statement is, an ideal Bose gas in d dimensions obeys the dispersion relationship Ek is equal to Ak power s. Here A and S are the constants. For Bose-Einstein condensation to occur, the occupancy of the excited state, where C is a constant, should remain finite even for mu is equal to 0. So this can happen only if, so okay, so let's try to figure it out which one is the correct option. So we are given that Ek, that is equal to Ak power s. Here A and S are given to be constant. A and S are constant. Okay, now the occupancy of the excited state, is given by n of E, that is equal to a constant C from 0 to infinity, and then e power d minus s upon s divided by the a power minus 1 exponential beta e minus mu minus 1, okay, and then dE. Okay, let's call this as equation 2, because here it's given that mu is equal to 0, where a, in principle, a is equal to exponential mu upon kt, and this is equal to 1 in this situation. So that's why it's not there in the given integral. So this quantity is equal to 1 in principle here for the given situation. Now the number of particles they are given by, it's basically the number of particles, that's Ne, that is equal to 0 to infinity, that's the probability distribution function Fe, and then Ge dE. Okay, this is the density of states in the range, that's the density of states. Okay, so let me call this as equation 3, and Fe, that's the Bose-Einstein distribution function. Fe, that is equal to exponential beta e minus mu minus 1. Okay, so here we are going to discuss the case of three-dimensional relativistic and non-relativistic particles, as Bose-Einstein condensation, it's not feasible in 1D and 2D. Okay, so we will discuss the case of 3D, okay, relativistic and non-relativistic. Okay, so for the first case, the case 1, for the relativistic particle, for relativistic particles, that is photons, you can say the dispersion relationship is E is equal to PC, or P is equal to E upon C. Okay, so the correspondingly the number of microstates with the momentum less than equal to P, that is equal to the available phase space, that is V multiply by 4 by 3 pi P cube divided by the volume of one cell. Okay, so that is equal to H cube. Okay, so this implies this expression in terms of energy reduces to omega E, that is equal to 4 pi V upon 3H cube into E by C. So we have derived this result directly from here by simply making this transformation, P is equal to E by C. Okay, now omega dash E, that gives the density of states in the energy range E to E plus D. Omega dash E, that is equal to d omega E upon dE into dE, and that is equal to 4 pi B upon C cube H cube E square dE. Okay, and that is nothing but GE dE. Okay, so therefore NE is equal to C from 0 to infinity. Now we will substitute the value of GEDE here in this expression, and then the value of the distribution function, and then we will obtain a result that's identical to this one. Okay, this is this equation 2 is a general result, but now by considering a particular case of relativistic particles, now this we will compare the equation 2 and the obtained results, and then accordingly we will predict the value of dys from there. Okay, so for this case, this expression reduces to E square, okay, divided by exponential beta E minus mu minus 1 and then dE. So here this constant, see, it absorbs all the 3 multiply coefficient here. Okay, so I'm keeping only the energy dependence term inside the integral. Okay, let me call this as equation 3. Now we will make a comparison between equation 2 and equation 3 and then try to see that what is the correlation between dys and the corresponding numerical value. So if we compare equation 2 and 3, 2 and 3 implies that a comparison of the integral, so e square, that is equal to e power d minus s upon s. Okay, so that means you just compare the exponents, that is dys minus s upon s, that is equal to 2. So this implies dys is equal to 3, which is greater than 1. Okay, now for the second case, we will consider the non-relativistic particle. For non-relativistic particle, we will repeat the same calculation. For non-relativistic particle, okay, the energy is given as E is equal to P square upon 2m. Okay, so that omega P, that is equal to 4 pi B by 3 h cube and then multiply by p cube. Okay, so this implies omega dash p, that is the number of states or the microstates in the momentum is p2 p plus dp. So this is equal to d omega p upon dp multiply by dp, and that is equal to 4 pi b upon h cube p square dp. Okay, and this can be further written as p into p dp. Okay, so because p square by 2m, that is equal to e, or I can rewrite this as p square is equal to 2m e. So that means 2p dp, that is equal to 2m de, or p dp, that is equal to mde. Okay, so we will make this substitution in the integral. So now from this expression we can quickly calculate the corresponding microstates in terms of energy omega dash e, that is GEDE basically. So that is equal to 4 pi b upon h cube. So I'm making use of this expression to transform this in terms of energy. So p squared dp, I will replace it with p dp, so that instead of p I will write 2m e power 1 by 2, that is p, and then p dp, that is equal to m de. So here it's the same thing, e. Okay, so after doing the rearranging the terms, so this is equal to 2 pi b upon h cube, okay, and then 2m power 3 by 2 e power 1 by 2 de, and that is nothing but ge de. Okay, so now let's substitute this value in the general equation that I wrote on the previous page. So that means here in this expression. Okay, so by doing that we obtain the expression for Ne, that is equal to a constant. Be constant absorb all these constant terms here. Okay, see, and then from 0 to infinity, e power 1 by 2 divided by e power beta e minus mu minus 1 de. Okay, so let's call this as equation 4. Now make a comparison between 2 and 4. 2 and 4 implies that e power 1 by 2, that is equal to e power dys minus s by s. So a comparison leads to a comparison between the exponent gives us a value of dys minus 1, that is equal to 1 by 2, implying that dys is equal to 3 by 2, again which is larger than 1. So based upon these conclusions, so we arrived at the final conclusion that C is the correct option here. Okay, so here C dy s greater than 1, that is the correct option here. Okay,